U substitution, covered in chapter 5, section 5, is one of our methods of integration that was covered last semester, but I'm going to review right now. It's sometimes called the substitution rule, and sometimes we called it U substitution. Same thing. Basically, U substitution can be thought of as running the chain rule backwards. If I was just to write out the chain rule very quickly, when we have a situation where we can visualize the function to be differentiated as being a compound function, f of g of x, take the derivative of that, that is the chain rule, and we can write it as f prime of g of x times g prime of x. Now if this is true, and it is, that's the chain rule, we could just integrate both sides to smush this in just a little bit. Like that, and that must be true. Notice this term here, we have a derivative within this integral, so what this comes is they cancel out and we simply get f of g of x is equal to this integral f prime of g of x g prime x dx. Okay, now this is the substitution rule we're going to use, and basically it says that our integrand, this inner part here, must be able to be written in this term. What the important things to note here is, number one, you've got some function within another function. Compound function, some f prime, can be almost anything, but within it we get g of x, and then the second thing that's very important is multiplied by it, this multiplied by this, and this is going to be the derivative of that. So if that's true, and we know the antiderivative of f prime, in other words, we know what f is, we can calculate it, then we're done. We've got our answer. Sometimes this here is written in terms of, you might see it written like f prime of u du, like that, and that would be okay to do as well. And sometimes they might put in a capital F and no prime, or they could put in a big F. It's not really important what you do there, but this is the u part of our u substitution. And let me do an example to kind of show you how we'd run with this. And this is example 1 from the book, and it's integrating a simple little function, 2x plus 1 raised to the 1/2 power dx. So we look at this and say, well, it's got to be of this form, right? It's got to be, there's some function within a bigger function, so there's a compound function times the derivative. Well, we look at this and say, well, pretty clearly, here's a function, 2x plus 1, and that's setting inside of a larger function, square root. So that's good. But at least temporarily, we're not sure where our du term is. We've got u, so whenever I do a u substitution, I always write out u is equal to something. And sometimes you have to guess. They get more difficult than this problem, for sure. And sometimes you have to start over. But for this time, u is going to be equal to 2x plus 1, and that means that du, just differentiate this, is equal to 2 dx. Now, we go back over here and look, well, there's our dx, and that matches. In fact, it always matches, but there's no 2. Well, we can pull a little trick here and say, well, all I'm going to do is put in a 1/2 like this, and then I'll substitute in a u, 1/2 du, and if you look at this, if you put in u, we get 2x plus 1. Yeah, that matches. We put in du, we get 2dx, which doesn't match, but wait, here's my 1/2 multiplied by this, and we're good. So let's integrate this. We get 1/2 times u raised to the 3/2 power divided by 3/2. That's by rule. Then this is in the denominator, so we simply take the reciprocal, multiply by the numerator, so we get to the 2/3, u to the 3/2, and the 2's cancel, so we get 1/3 u raised to the 3/2. Of course, we wouldn't leave it in this form. We go back to our table that we wrote up here, where we'll always have u written out. So we just substitute the x term back in. We get 1/3 2x plus 1 raised to the 3/2 power. And of course, always, my pen would work. For some reason, it's trying not to work. Plus a constant. For some reason, Marsh, my pen has stopped working. So let's see here. Can I fake it? I'm faking this. Yeah. It's hard to fake. Very good. And that's our answer right there.